All right, so in this video we are going to look at using the second derivative test to find local extrema. What does local extrema mean? Think to yourself. Local extrema means relative, or could be global or absolute. Relative or local mean the same thing. Maximums and minimums. Here's how you're going to do it. You are going to use the second derivative test today, but you can also always fall back to the first derivative test to determine if you have local extrema. We're going to do both here so you can see how they compare. But for using the second derivative test, the second derivative test tells us about the concavity of a graph. And if we know that the second derivative is positive, if the second derivative is positive, and we went over this in the last video, if the second derivative is positive, then f, it implies that f is concave up in that region, meaning it's like a cup. If the second derivative is negative, it implies that f is concave down, like a frown. Like that. So we're going to use that to help us find extrema. And to find our local extrema, our local minimums and maximums, we want to figure out where the first derivative is 0 or undefined. And what we're going to do is we're going to look at, when we do this, we're going to be finding our critical points. And then we're going to check at those critical points whether the first or the second derivative is positive or negative. So if the first derivative is 0 and the second derivative is negative, then f will have a local maximum at that value. If the second derivative is negative, it means it's concave down, which is what we just went over. And if the graph is concave down and the derivative was 0, it means we have a horizontal tangent there. It means that you would have a local max at that point. And conversely, if the first derivative is 0 and the second derivative is positive, that means it's concave up. And if our derivative is 0, it means we have a horizontal tangent. So at that value, we would have a local minimum. So here's what we're going to do. We're going to find the first derivative to find our critical points. We're going to find the second derivative and plug those critical points into the second derivative to determine if it's positive or negative. If it's positive, we have a local minimum at that value of x at that critical point. And if it's negative, it's concave down and we have a local maximum. But you do need to note this. The test fails if the second derivative is 0 or does not exist. And if that happens, what we have to do is go back to the first derivative test to find our maximums and minimums. All right, so let's do a couple of examples here. First one, you should write this down and do this with me. Find local extrema for f of x. And I'm going to do it in using the second derivative test, and I'm going to use the first derivative test to show you the difference between the two. So step one for this, to use the second derivative test. Find critical points. How do you find critical points? Well, we want to figure out where the first derivative is 0. So we're going to find our first derivative. It's a power rule here. We get 3x squared minus 12. This is equal to 0. Solve that for x. I'm going to add 12 to both sides and divide by 3. Get x squared is 4. Take the square root of both sides, and don't forget when you take the square root of this side, you want to do plus or minus the square root of 4. So I have critical points of positive and negative 2. These are my critical points. to find whether they are maximums or minimums or neither, what we're going to do is we're going to do step 2. Find the second derivative and evaluate it at the critical points. And determine what's called a step 3. If f double prime of that critical point is greater than 0, there is a local minimum, because it would be concave up. At C. That says min at C. If the second derivative is negative for that critical point, there is a local max, because it would be concave down. You'd have like a hill, and at the top, that's where your maximum would be. All right, so let's do step 2 here. Move this up a little bit. Step 2, find the second derivative. Always put a box around your derivative and make sure it's labeled as the first derivative, and then our second derivative here, because a lot of times in these problems you're going to have to go back and find it, so it's nice if it's in a box or something, circled, something like that. Alright, so we're taking the derivative of this, which is 6x. So now we want to evaluate at our critical points. So at the second, if the second derivative is evaluated for x equals -2, we get 6 times -2, which is -12, which means we're here. The second derivative is negative. It means that it is concave down, so you would have a local max at x equals -2. Let's do this for +2, and then we'll write that solution out. So at +2, we have 6 times +2, which is +12, and we're at this. We have, if the second derivative is positive, which we have, then there's a local minimum, because it's going to be concave down there. You're going to have a local minimum at that value. So critical points, there is a local minimum at x equals +2 and a local maximum max at x equals -2. All right, I'm going to graph. So here is the graph of our original function. What I have in y equals is the original function that we started with, f of x equals x cubed minus 12x minus 5. Looking at this graph, we have a local maximum at -2. You can see the cursor there. And at +2, we have a local minimum, which confirms what we found. Okay, we're going to do this same exact example, but we're going to use the first derivative test, and just to show you the difference here. And you can decide which one. You can use either, but sometimes it's going to be more convenient to use the second derivative, and sometimes it's going to be more convenient to use the first derivative test. Okay, so first derivative test. We're going to find extrema using the first derivative test. If the second derivative is difficult to find, you don't want to, it's going to be easier to use the first derivative test. But here's what we do. We find where our critical points are, which we already did this. We got 3x squared minus 12 critical points at ±2. Now we're going to do the interval. So we're going to break up our x-axis by these critical points. So we're going from negative infinity to -2, then from -2 to 2, and then from 2 to infinity. Not to 8, to infinity. All right. What we do for the first derivative test is we pick a test point, and then we test it in the first derivative, and we decide if it's positive or negative. If it's positive, it means f is increasing. If it's negative, it means f is decreasing. And if we go from increasing to decreasing, we have a maximum. If we're going from reverse that, we have a minimum. So, all right, so pick a test point. I'm going to pick -3, 0, and +3. So you guys should do this yourselves. Plug it into the first derivative, determine the sign of the first derivative. All right, so for finding f prime of -3, you plug in -3 for x and evaluate it. You get 27 minus 12, which is, I don't really even care what the result is. All I need to know is it positive or negative. That will be a positive result. And what it means for the graph of f is that f is increasing, because if our first derivative is positive, the slopes are positive values, and so it means the graph of f is increasing for that entire region. And if we look at our graph, it is increasing that entire time. And then between -2 and 2, I picked 0, or you always want to pick the easiest number you can. When I evaluated f prime of 0, I got 3 times 0, which is 0. 0 minus 12 is going to be a negative. I don't need to know the exact number, I just need to know if it's positive or negative again. It's a negative value. When the derivative is negative, it means f is decreasing. Your slopes are negative, so it's decreasing. And then finally, f prime of 3 was also -12, which you could have, it's going to be the exact same value as this because it's an even function. So the even function, if you put in a positive or a negative, you get the same result. So it is increasing there. So if it's going from increasing to decreasing, you have a max at -2, which is the same as what we got with the second derivative test, and we have a minimum value at +2. So either test works. Use whichever one is easier, and if you have enough time, you can do it both ways to check your results.